Hello, today we're going to look at digital sampling, signal spectra and bandwidth for A-level physics revision. We're going to start with digital recording, and we really need to go back to basics and say what actually happens when you take a microphone and you have sound coming in and you have an electrical signal coming out. What is actually happening inside the microphone? Well, of course, the sound is coming to you in sound waves. Sound waves are longitudinal waves. So in other words, instead of vibrating as electromagnetic waves do as a sine wave in this way, they actually vibrate in and out. So at any moment of time, the air, for example, through which the sound is traveling will be either very compressed or it will be rarefied. Typically, if you look at the sound waves, you will find that it gets rarefied and then it spreads out and then it becomes rarefied again and then it spreads out and it's rarefied again. But that's constantly changing so that the air is vibrating but in a longitudinal way as the sound waves cause it to vibrate. Inside the microphone, in essence, is what's called a diaphragm, and you can think of a diaphragm as really stretched piece of balloon skin. And there it is, and in the middle is a small magnet, and around the balloon skin is a coil of wire. Now sometimes it's the other way around. Sometimes they put the coil of wire on the balloon skin and they have a magnet outside. But here's the way it works. When the sound waves, which are causing the air to oscillate in this fashion here, when they hit the diaphragm, I'll call it a diaphragm now, they cause that to vibrate. And as that vibrates, the magnet also vibrates. And now you've got a moving magnet in a coil, or alternatively, a moving coil in a magnet, depending on which way it's been done. And wherever you have a moving magnet or in a coil, you will get a current flowing. And so in this coil, a current will flow. And the size of that current will reflect the degree of movement of the magnet. We've done this in electromagnetism. So you've got a current that is essentially analogous to the sound wave that caused it. And that's why it's called an analog signal. Now just think about the sound you might be recording. Say you're recording an orchestra, then although the waves are not sine waves, as I've said, in terms of the fact that they're not transverse, they're longitudinal, nonetheless we can represent them as sine waves. So if you took something like a flute, which is playing a very high pitch means high frequency, so a flute's frequency would look something like this, where this of course is the amplitude of the frequency and this is time going by, and so you've got a very short wavelength, high frequency wave, whereas a double bass over time would look like that because, and this is again is the amplitude, because the double bass is a very low note, and that means its frequency is much smaller, and that means its wavelength is much longer. And all these frequencies, this is just two instruments from the orchestra, but sound waves have the capability of what's called superposition. As all those sound waves approach the microphone, they are effectively all joining together and making an amalgam of a wave. So if we just simply add the double bass and the flute together, then you're probably going to get something that looks like this. You know, you've got the double bass, which is the longer wavelength, superimposed on which will be the flute signal. On this basis, the flute is much softer than the double bass. If the flute were about the same volume, then you would get a kind of pattern that looks like this. But you've got all the other instruments of the orchestra, and those waves are hitting the diaphragm and they are creating a pattern which will look like this in terms not now of sound waves, but once you've got the current coming out of here, you've got current and obviously voltage. So if you were to measure this on a cathode ray oscilloscope, CRO, then this would essentially be the voltage or the current, and this would be time. So this now becomes the electrical analog signal of the sound waves that caused it. And in the old days, you would send that electronic signal that you got from your microphone to a reel-to-reel tape recorder, which had a reel-to-reel would have a tape. The tape would have an iron deposit on it, and you would go past what were called the heads, and the electric current from the microphone would be fed into the heads, and they would cause the iron deposits on the tape to form a particular shape, and that therefore you will have stored, in a sense, the sound analog signal on the tape. And then when you play it back, the tape will cause the heads to recreate the current that caused it, and you can take that current off to a loudspeaker and play back the sound that you started with in the first place. Initially, of course, this process was fraught. All sorts of noise and irregularity was introduced, and so the designers of these systems were always trying to get the best and the most faithful reproduction of the sound. They were looking for the fidelity, if you like, the faithfulness of the sound, and the higher the fidelity they could get, the better. Consequently, they were looking for high fidelity, or as we shortened it, hi-fi. So as I said, if you were to look at the signal that comes out of the microphone, which is an electrical signal analogous to the sound signal that caused it, here's a cathode ray oscilloscope. The vertical axis is going to be, depending on what you look at, the voltage or the current, and so this is voltage or current going upwards, and you just have a time base going across. So you're actually seeing how the wave changes, or how the current changes with time, and you get what essentially just looks like gobbledygook on the cathode ray oscilloscope, because that is the amalgamation or the superposition of all the sound waves that have contributed to the sound that the microphone has picked up. And this pattern, of course, is constantly changing with time, so you will just see it constantly moving. Now, one way of overcoming the fact that to this analog signal, all sorts of noise can be added, and when you record it on the tape, you lose some quality, and when you play it back, you lose some more quality. What you can do is to digitize it. And this is the way you digitize. You, as it were, freeze frame this shape. So just essentially stop it for a moment. And let's suppose that you get something like this. What you do is you superimpose on that a grid. Computers are good at doing this sort of thing. And let's suppose we have, what have I got here? 1, 2, 3, 4, 5, 6, 7 lines. And let's separate the grid up like this. And it's a bit like the pixels in the photograph. What you're going to say is that for each square, we are going to look and say, what is the, as it were, average current in that square? So, for example, here we would say it's this one. Here we would say it's maybe this. Here we would say it's maybe this. Here we would say it's maybe this. Here we would say it's this. Don't criticise my kind of assumptions. Computers do this much better than I can. Here we'd say it's this. Here we'd say it's this. So we've now got the average, or not the average value, the value per square. And this is 1, 2, 3, 4, 5, 6, 7. And so the digital value of that signal would be represented as 4, 6, 1, 5, 2, 3, 1, 1. Okay, that is the digital value of that signal. Now, clearly, you can see that that means we would get a signal that was 4, 6, 1, 5, 2, 3, 1, 1, 1. And that doesn't look very much like this. But I think you'll agree that if you make the divisions much narrower in both directions, then you will get to a point where the digitized signal is very close to the analog signal that you were measuring. So we've got a problem here. It's a trade-off issue. If you have too few gradations, too few of these, as it were, pixel equivalents, then you're not going to reproduce the sound in the digital signal that was the original analog. But if you have too many, then of course, remember, every single one of these is going to be depending on how many gradations you have, you're going to need a number of bits to retain each of these numbers. Then that is going to overload your computer. You're going to have a massive amount of data to process and a massive amount of data to store. And the way this is resolved is that for CDs, the vertical component, in other words, the number of levels that you split your signal up into, the voltage signal, is 65,536. And that is equivalent to 16 bits or 2 bytes. So what you essentially do is to divide this up into lots of different levels, and you give each of these, in each column, you give one value which represents the level of the signal at that point. And that can be anything from 0, if there's no signal at all, to 65,536 if it's at its, as it were, its maximum volume. And each of those numbers therefore needs 2 bytes in order for 65,536 gradations to be achieved. Just to remind you, this is, as it were, the voltage or the current, and this along here is time. So these divisions represent the amount of time that we're going to elapse between each sampling of the wave. And this way is called the sampling rate. This way is called the digital resolution. So the digital resolution is 65,536 different alternatives, levels if you like. This rate is called the sampling rate. And the sampling rate for most CDs these days is 44,100 Hertz. In other words, you measure the level of the current or the voltage 44,100 times per second. Now, how did they determine to use this number for the digital resolution, in other words, the number of gradations this way, and this number for the sampling rate, in other words, the number of gradations per second, that way? Well, let's take the bit resolution or the digital resolution first. You can have too many gradations, ironically. Let's suppose that you had a signal that looked like this, and you want to set up the number of gradations by which you're going to measure. So you're going to define the level of the voltage at each point to that level of resolution. Well, it's quite possible that noise will be added to the signal, and you might actually get a signal that looks like and if you have these too close together, you'll start to identify the noise resolution. And the last thing you want is to reproduce the noise in the digital signal. And so what you do is you look at the total voltage difference, which we call VT, in other words, the complete range of the voltage or the current. And you look at the range of the noise, which we'll call V noise. And there is a formula which has been developed by the digital recording experts, which is that the maximum number of bits that you need, that is, to record this number of gradations, it turns out it comes out to about 16, so you can get the 65,000 different alternatives, the number of bits you need is log to the base 2 of the total variation of the voltage divided by the variation according to the noise. And that actually comes out to 16 bits, approximately 16 bits. If you do any more than that and you think you're getting an even greater quality, what you will actually do is to start sampling or to start measuring the degree of noise, and you can do without that. Now, what about the sampling rate, which is the number of times per second that we measure the voltage or the current? Well, let's suppose that the actual signal, this is the analog signal, looks something like this. So we've got actually quite a high frequency signal coming in. But let's suppose we sample it here. So this is a time signal, this is the voltage. So this is how the voltage is varying with time. So we'll sample it at this time here, then we'll sample it at this time here, then we'll sample it at this time here, then we'll sample it at this time here, and then we'll sample it at this time here. Okay, so we're doing regular sampling. That's supposed to be reasonably regular. So we take a sample snapshot at that point, at that point, at that point, at that point, at that point. What will that digital picture look like? It will look as though we've got a wave that looks like that. That's a very long wave, a very low frequency. So ironically, with a very long sampling period, you can convert high frequency sounds into a low frequency wave. So you have to be able to take these samples sufficiently frequently that you don't get that kind of mistake happening. And the general rule is that you need to take the frequency of sampling has got to be twice that of the highest frequency sound that you're likely to record. Now, the highest frequency that the human ear can usually hear is about 20 kilohertz. And that tends to be young people. As you get older, the top range reduces, and for older people, generally 16 kilohertz is the maximum they're likely to be able to hear. But since we're going to be recording for young people, we must take that into account. So if 20 kilohertz is the highest frequency you're recording, then the sampling frequency has got to be double that, which is 40 kilohertz. And as I've said, what they've actually used for various technical reasons is 44.1 kilohertz, or 44,100 times per second. Different systems use different rates. Some go as high as 96 kilohertz. But of course, what you've got to think about is that the more times you do it per second, the more data you're going to receive. So how much data is there going to be when we digitize a 3-minute song? So let's take a 3-minute song. Well, we've already said that we're going to sample 44,100 times per second. So every second you're going to do 44,100 measurements. Each of those measurements is going to need 16 bits because we're going to have 65,000 alternative values for the level of the voltage. So we're going to need 44,100 samples per second times 16 bits for each sample. We're going to record in stereo, so you need 2 times that. And of course, this is just per second, and we're doing it for 3 minutes, which is 180 seconds. That will tell us the total number of bits we need. But of course, there are 8 bits per byte. So we can convert this now to bytes. And if you work that out, it should come to 32 megabytes. So you need 32 megabytes of storage to store the information that is coming from a 3-minute song. So what's the advantage of digitizing a signal? Well, digital signals can be sent and received and reproduced more easily because once you've digitized the signal, you can never corrupt it unless you, of course, do something drastic. But you can't add noise to a digital signal. It's either a 1 or a 0. It can't be anything else. You can use digital signals to represent different types of information. We've already shown how digital signals can be used for images in another video, and here we're using digital signals for sound. And of course, because we're talking about digits, we can process those easily on computers because that's what computers do best. They process binary digits. But of course we have to recognise that since you're digitising, you can never exactly reproduce the original signal, but in fact you can do it sufficiently well that it achieves what you want to achieve. Now we're going to look at how we transmit information. Well, let's consider a signal. Here of course we're looking as usual at the voltage, and here we're looking at the frequency. This is of course against time. And so we will have a high frequency and a low frequency, and what's called the bandwidth is the gap between the lowest frequency or the highest frequency minus the lowest frequency. So if you're talking about sound, the highest frequency is likely to be about 20 kilohertz, and the lowest frequency, well, that might be 100 hertz or maybe 50 hertz. So you might as well say that the bandwidth is 20 kilohertz, because that is the difference between the highest and lowest frequency. When it comes to television signals, that's for sound, that is here. If you're talking about television signals, then you need to obviously contain a lot more information, and that the bandwidth for that tends to be 8 megahertz. And the way that signals are transmitted over the air is to use a carrier wave. So what will typically happen is that a sine wave, carrier wave, electromagnetic wave, usually in the radio wave of the spectrum, VHF or UHF, sometimes short wave, of course sometimes medium wave, sometimes long wave. And then what you do is you add to that the actual signal that you're trying to send. So the signal will be superimposed on the band wave, on the carrier wave rather. So it looks something like this. The signal is embedded within it. When you get to your television or your radio, that will use essentially the LRC circuit that I described in another video, and that will be able to tune itself to the wavelength that this carrier wave has. And once it has received, you get what's called resonance with an LRC circuit. It picks up this wave more than any other that might be floating around in the atmosphere at the time, and then it strips off the carrier wave and leaves just the basic signal that you had in the first place. But there is of course a problem which we know about waves, and that is that they are capable of interfering. So if we have a transmitter here and a transmitter here, and they are both transmitting signals at the same wavelength, and you're standing here with your radio will pick up both signals, but there will be an interference between them, and so it's likely that you will get a combination of the two programs, and that will not be making very comfortable listening. So within this area here, you're going to have very bad interference. Consequently, you have to make sure that the carrier wave coming from this transmitter is significantly different from the carrier wave from that transmitter. And in fact, the idea is that you try to make sure that they are at least one bandwidth apart. In practice, you probably find that the carrier waves are significantly different in wavelength to ensure that there is no interference. In terms of television in the UK, the bandwidth, or rather the spectrum that has been allocated, radio frequency spectrum is a very scarce resource. There's only a limited amount of it, so it has to be used carefully and sparingly. But in the UK, the electromagnetic spectrum, which has been set aside for television broadcasting off air, that is where you've got a transmitter on the ground as opposed to a satellite, is 470 megahertz up to 860 megahertz. And I said before that the bandwidth was 8 megahertz, that is the frequency bandwidth to contain the entire signal. And what that means is that this bandwidth of, or rather frequency spectrum of the electromagnetic spectrum contains 48 channels. So you can only send 48 different, as it were, wavelengths of carrier waves, and those are numbered 21 to 68. So BBC, ITV, Channel 4 all get a channel, and they are allowed to broadcast on one of these channels, which will be 8 megahertz wide. Now in practice, you might think you can only therefore have 48 transmitters, each transmitting one of these channels, but actually you can do better than that, because if you think about if this is England, you might have a transmitter in Newcastle and a transmitter in Exeter. Well, they might transmit on the same channel, because by the time the signal from Newcastle has got all the way down to Exeter, it's going to be so small, it's going to be almost undetectable. So the interference is going to be trivial. But you couldn't have two transmitters almost side by side transmitting on the same channel, because then you get interference. So you can reuse the channels as long as you're far enough away. As far as radio is concerned, then the typical bandwidth that has been, or the typical spectrum that's been allocated, is 30 megahertz to 300 megahertz. For example, BBC Radio 2 is 88 to 91 FM, as they call it, which is 88 megahertz to 91 megahertz. The bandwidth required for each channel is 0.2 megahertz or 200 kilohertz. And so you can see that you've got a total spectrum of 300 minus 30 megahertz. Each channel is 0.2 megahertz wide, so that gives you a total of 1350 stations. I'll just write that here. 1350 separate channels in this spectrum here. So again, you might think that you're limited to only 1,350 radio broadcast channels, but actually again that's not entirely true, because you can repeat some of these if you are far enough away. The same frequency can be used for transmission, because they're so far away that the intensity of the signal from one will be trivially small by the time it reaches the other. So actually you can have more than 1,350 radio stations. But if you want to transmit in digital, let's just think for a moment about what that means. How many bits are you going to have to transmit in 1 second? So what will your computer have to process if you digitized all this sound? Well, we said that there are 44,100 samples per second. Each of those requires 16 bits. We're going to broadcast in stereo, and so that is the number of bits per second that you're going to need to be able to transmit. Your computer's going to have to be able to process that amount, and of course, as we said before, you can divide that by 8, and that now gets you the number of bytes per second that has to be transmitted. So you need computers with a fair degree of processing power to be able to just push that out at that rate across the airwaves. Although the waves are not sine waves, as I've said, in terms of the fact that they're not transverse, they're longitudinal, nonetheless we can represent them as sine waves. So if you took something like a flute, which is playing a very high pitch means high frequency, so a flute's frequency would look something like this, where this of course is the amplitude of the frequency, and this is time going by, and so you've got a very short wavelength, high frequency wave, whereas a double bass over time would look like that, because, and this is skin, and there it is, and in the middle is a small magnet, and around the balloon skin is a coil of wire. Now sometimes it's the other way around. Sometimes they put the coil of wire on the balloon skin and they have a magnet outside. But here's the way it works. When the sound waves, which are causing the air to oscillate in this fashion here, when they hit the diaphragm, I'll call it a diaphragm now, they cause that to vibrate. And as that vibrates, the magnet also vibrates. And now you've got a moving magnet in a coil, or alternatively, a moving coil in a magnet, depending on which way it's been done. And wherever you have a moving magnet or in a coil, you will get a current flowing. And so in this coil, a current will flow. And the size of that current will reflect the degree of movement of the magnet. We've done this in electromagnetism. So you've got a current that is essentially analogous to the sound wave that caused it. And that's why it's called an analog signal. Now just think about the sound you might be recording. Say you're recording an orchestra, then hello, today we're going to look at digital sampling, signal spectra and bandwidth for A-level physics revision. We're going to start with digital recording, and we really need to go back to basics and say what actually happens when you take a microphone and you have sound coming in and you have an electrical signal coming out. What is actually happening inside the microphone? Well, of course, the sound is coming to you in sound waves. Sound waves are longitudinal waves. So in other words, instead of vibrating as electromagnetic waves do as a sine wave in this way, they actually vibrate in and out. So at any moment of time, the air, for example, through which the sound is travelling will be either very compressed or it will be rarefied. Typically, if you look at the sound waves, you will find that it gets rarefied and then it spreads out and then it becomes rarefied again and then it spreads out and it's rarefied again. But that's constantly changing so that the air is vibrating but in a longitudinal way as the sound waves cause it to vibrate. Inside the microphone, in essence, is what's called a diaphragm, and you can think of a diaphragm as really stretched piece of balloon